name's Dave DeBoer. I'm one of our business development managers in the Aerospace and Defense Group for Microchip. And today I'll be talking about kind of a big broadcast of radiation types, their sources, and then some of the parts we make that kind of deal with those radiation sources and types. So let's get started. So first of all, once you leave our atmosphere, you get exposed to different types of radiation. And there's several types of radiation that can affect semiconductors. The first type would be from the electromagnetic spectrum. The next type would be subatomic particles. And so if we jump back up to the electromagnetic spectrum. So the electromagnetic spectrum contains frequencies that start with long wave radios, moving up to microwaves, into like infrared type products, visible light. Of course, within there, before the visible light, is the frequency that's critical to every teenager, which is broadband for G for your cell phones, and then moving up to ultraviolet, and then into X-rays and gamma rays. And really, from the electromagnetic spectrum, the two frequencies that matter the most are X-rays and gamma rays. The subatomic particles that can affect semiconductors when we get into space are alpha particles, beta particles, ions, which are usually referred to as heavy ions, and then protons, electrons, and finally neutrons. And then here comes the particles, one at a time. Not the last one. So a clever way that I kind of created to help you remember the types of radiation that affect semiconductors in space is an acronym I came up with. And the acronym is Hackster Gripen. And so the breakdown of the acronym is B for beta, A for alpha, X-ray, for X-ray, and that's your Hackster. And then Gripen would be GR for gamma rays, I for ions, P for protons, E for electrons, and then N for neutrons. And so it's just a kind of a clever way to, remember the types of radiation. Hey, Hackster Gripen is a great party gig, right? So anyways, I created a mascot, and it just happens to be my Schnauzer, which is a German Schnauzer, because Hackster Gripen sounds German. So anyway, so moving on. So what kind of space sources of radiation are there? So the source that is our solar system, and the other one is outside our solar system, which is the galaxy. In our solar system, the primary source is the sun. And the sun creates things like solar wind, solar weather, also solar flares, and coronal mass ejections. The other source in our solar system would be the Van Allen belts. The Van Allen belts are basically these belts that wrap around the planet Earth, both inner and outer belts, that hold different types of radiation around the planet. And so as your satellite flows through these Van Allen belts, they get exposed to radiation. In the galaxy, there's things called galactic cosmic rays. And these are particles that are emitted when you have different events throughout our galaxy. And these events would be things like a supernova, which would throw a lot of these particles throughout our galaxies and eventually making its way to our planet and solar system. So those are the sources of radiation, the solar system and then the galaxy. Now, what kind of concerns do we have for our semiconductors when they're in space? So the first concern would be a cumulative effect that happens over a distance of a period of time. And the radiation types that accumulate over a period of time would be gamma rays, X-rays, and then alpha particles. So this accumulation is what we would call total ionizing dose, what you may hear as an acronym TID. So what this effect does is it actually charges get trapped in the device's oxide. And what that does, what that charge will do, is it'll actually decrease the voltage threshold that your transistor switches at. So as you can imagine, your transistor switching at a different threshold would be, not good. The other thing that can happen is the off state of your transistor, the current will start increasing. So it will not be completely off. And so you can imagine your current demand would go up, and eventually your transistor would never appear to open, which could be not good. The other types of accumulative effects would be displacement damage dose and total non-ionizing dose. So these also cause a type of material degradation of your semiconductor. And primarily the parts that we're concerned about with triple D and TNID would be things like bipolar transistors, solar cells, LEDs, laser diodes, and then optocouplers. Now, what about shielding? Can I shield for these? So luckily, there is some methods to shield some of the cumulative effects, but you still have to be concerned with the effects of TID, triple D, and TNID. The next type of radioactive effects come in kind of a bad form, which would be both destructive and non-destructive effects. And these come from particles usually. These would be protons, heavy ions, and then neutrons. So they come in terms of what we call single event effects. And they are both, like I mentioned, destructive and non-destructive. A destructive effect could be a single event latch-up. The next destructive effect could be a single event gate rupture. And the last one would be single event burnout. Now, with a destructive event in a semiconductor, that would mean most likely the device would be failed and no longer function, or function completely erratically, so not as designed. The other type of effects, which are non-destructive, are single event transients, single event upsets, single event bit upsets, multi-bit upsets, and then multi-cell upsets. Now, the nice thing about these upsets and events, if you cycle power, you can actually reconfigure your device to bring it back to its normal functionality. Unlike a destructive effect, cycling power doesn't do anything. It's been destroyed. Unfortunately, for these type of radioactive concerns, you cannot shield for SEE particles. So no matter what you do, no matter where you place it in your spacecraft, you can't shield for these. These will hit your semiconductors, and some will be destructive. For Microchip as a whole, we design parts both for radiation hard, where the energy levels of both the cumulative and destructive effect are a lot higher. And then we also design parts that are rad tolerant, where those levels are a lot lower. And the real difference between a radiation hard and a radiation tolerant part is going to be your mission and what type of orbits you're flying in, whether it's a low Earth orbit or a mid-Earth orbit or geosynchronous or interplanetary. There's lots of different orbits and inclinations and the whole gamut. And so Microchip offers an excellent spectrum of devices that cover that entire product category. And what I've done is I kind of highlight all our product offerings. And the dark blue colors are basically the space products, both RT and RH. And then the lighter blue would be the rest of the aerospace and defense products and our terrestrial products. But in the dark blue, we have things like RFICs, mimics. We have timing products, both clocks, timers, atomic clocks, things like that. We do ADCs, memory products. We have encryption and security, DC to DC converters and supervisors and reference parts and LDOs, a whole battery management scheme. Our core devices are things like our microcontrollers, microprocessors, FPGAs, and system on chips. We also have support chips for Ethernet, motor drivers, and then power drivers. So this is a quick overview of radiation and some of the sources and some of the effects. And I sure hope you, at your next get together, you mentioned Baxter Griffin to your friends. So that's the summary of my talk today, and I hope you enjoyed it.
Our first question, are there any specific kits for evaluation for space applications?
Microchip does offer quite a few development boards and development kits for different type of applications, anything from motor drivers to microcontrollers and FPGAs. We have probably 6 or 8 systems that emulate what you might see on a spacecraft. And those are good systems. They usually combine 2 or 3 development cards. And they're a good beginner for starting building your system. So, but in terms of development boards, we have lots and lots of development boards. A lot of the RT products are upscreened from commercial automotive parts. So you can actually start with some of those devices and move up to the radiation tolerant devices that we have available for space.
Awesome. And what are the licensing requirements for developing with these devices?
Yeah, so most, if there is any licensing, it's usually associated with the software that may support that product. For an FPGA, there might be some licensing fees for some of the software platforms. And then also, if you are doing a microcontroller or microprocessor, there might be a licensing fee for those. You can reach out to any of the Microchip supporting reps or direct sales, and they can actually give you, what the cost is and for that system you're looking at, and provide you that information.
Thank you. And how do users know which products to choose for their applications, especially if they're not an astronaut and have never been to space?
Yeah, so a lot of times, most customers will have a mission profile, which will define things like their total ionizing dose, TID, or the amount of radiation they might be exposed to in terms of single event latch up. So our products, our RT and RH products, give you definitions on how they perform for TID, total ionizing dose, and for single event latch up. And so you can kind of pick the product that would work for your application. TID is, like I mentioned in the video, it's an accumulated radiation. And so if you have let's say a 5-year mission, and your total accumulated dose over that mission is, let's say, 25 KTID, then we have devices that are 30 KTID and above. So you would pick something with some type of derating, of course, that would meet your application. The other thing I mentioned is for things like TID and like single event particles, TID you can shield. So depending where your product is buried within the spacecraft, certain amounts of aluminum will provide an additional shielding. So you can actually use a part that may be a lower TID for your mission profile. But usually you target something that's close to the range your mission is expecting to see to guarantee you'll have success for your mission life.
Yes, and we had a question in the chat that former Actel had some radiation resistant FPGA. If is Microchip using similar technology, or is radiation resistant FPGAs, is there like an industry standard?
So when you develop a RT part, the RT parts are usually screened. So we have a for I'm just going to talk non-FPGA right now. For most of our RT parts, radiation tolerant, not radiation hardened, these are parts that we've evaluated, and we have a process we go through to evaluate our parts for radiation tolerance. And it's like a gating process, and there's a bunch of gates. So what we do is we simulate the device via some radiation testing tools. And then if they perform well there, then we would do some radiation testing. So based on single event latch of numbers, we have some process tunes, knobs we can turn to give better performance for single event latch up. And then we would reevaluate to see if we're hitting numbers that would be adequate for radiation tolerant. Usually we shoot for radiation tolerance. We usually shoot in that 60 MeV range. And then for TID, we usually shoot for that 30K TID. So after we do single event and it seems like it's adequate, then we would do TID testing to see how it performs in TID. So the summation, if it meets our criteria, then we would offer the part both in plastic and in ceramic, which are, it's depending on your environment, how much, you're willing to spend for the screening process, provide you an optimally tested part for your application. So going back to the FPGA. So we do use some of the libraries that were first developed for Actel. We have some AVR parts that are radiation tolerant, and then we've used radiation starting blocks or building blocks on a semiconductor level to build up a part that's fully radiation hardened. And we do have some rad hard parts, and rad hard parts would usually be in that 100K TID and usually above 78 MeV. So from the old Actel, we do have some libraries that we use to build up new parts. And some of those parts are some of our SAM parts. We have a SAM RH part. And the FPGA group, which kind of has its own library of parts for the FPGAs, has both radiation hard and then radiation tolerant parts. So their definition of radiation tolerant versus radiation hard is a little bit different than some of the upstream parts, but all in all, they still perform very well in space applications, and they would meet your mission profiles. And I see the Actel, Microsemi, and Microchip. I have another slide that actually shows all the acquisitions, because when we brought Microsemi, they had a whole bunch of companies that were dabbling in radiation hardened parts, things like discrete semiconductors, like MOSFETs. We do MOSFETs now, diodes, TVR, or TVSs, things like that. So yeah, we have quite an extensive library of parts we use and can sell for RT and RH.
Oh, we had another question in the chat.
Yeah, I'm looking at that. So what's the main effect seen in MOSFET transistors? So under X-ray radiation, it's usually X-ray is usually associated with TID. So what you would see for TID is your transistor would, accumulate dose and eventually fail to shut off. What you might see for a single event for particles is you could see what's called gate rupture. Some people will derate their parts and say, instead of using a 60 volt MOSFET, they'll use a 150 or 200 volt MOSFET for a lower voltage application. Now that doesn't guarantee that part's going to perform over period in space, especially for particles. So what happens is a lot of your MOSFETs are used for power directing, right, on the back end of a DC to DC, or in some power switching where you're providing power to certain boxes. What I would recommend, since it's usually a critical part, is either screening your parts for radiation tolerance to see how they perform, or using rad hard parts, even for a LEO environment. And the rationale is if your MOSFETs go, then you usually lose your power supply. If you lose your power supply, you will lose your spacecraft. So really important to use the right MOSFETs in your application.
Awesome. And we probably have time for one or two more questions if anyone
You bet.
has them. Or if there's anything you'd like to share now that you've heard a couple questions from.
Who, me? Yeah, basically to everybody out there, if you have any questions, I mean, feel free to send me an email, ask questions. There's a movement, as a lot of people are finding, that they want to use automotive parts in space, and the reason being, they think that the automotive parts are consistent, they're well controlled, and they're usually available for a long period of time. The one thing it doesn't guarantee you is how it'll perform in space. You know, it's a part. It's consistently built and maintained. It's high reliability, but you don't know exactly how it'll survive in a space environment. And so, you know, testing those parts and evaluating those parts is always critical. And then, you know, to build your confidence for your spacecraft, I would really recommend that you do some TID testing and single event testing to make sure you're comfortable with that part. Now, there's other strategies you can do in those spacecraft, but you can't have TID is probably a critical thing, especially if you're running single strings with your design. So triple majority voting, if you're doing a spacecraft, that's common, using backup systems and A and B side, so you're not single string. But all that comes with trade-offs of cost and efficiency and time and money. So a lot of things to consider when you're doing your evaluation for space. But people are looking at automotive and upscreening them for space and taking a little bit of risk with an automotive part versus just using an RT part or RH part. And it's all your risk tolerance too. Would you use it on a $100 million satellite? Probably not. On a $100,000 satellite, you probably have a higher risk tolerance. So things to think about when you're doing your design. But yeah, if you have any questions beyond this, feel free to send me an email.
We did have one more question come in about
and match with all the radiation effects combined. How do you triage the biggest risk versus risk overall? Yeah, that's a good question. Yeah, an analog's a completely different beast, right? So analog circuits, some will have BJTs. BJTs are something else you have to be concerned about. They have different failure mechanisms, and they could completely disrupt the performance of your analog circuit. So it's definitely something that you should test and vet. Let's see, match with all the radiation effects combined. Yeah, triaging the risk. So like I mentioned, the best way to triage is if you're in a high risk situation with using automotive parts, I would probably try to bury my semiconductors within the circuit, within the spacecraft, to give you enough metal protection to minimize your TID. And the other thing is to do maybe run dual redundant or triple majority type circuits that you can make a decision on the back end for how the device or the circuit performs. So Yeah, different strategies. It's going to be based on what your risk level is for the spacecraft and how much it's if it doesn't fail and meet its mission requirements, then it's like, well, did I not put something into space that was a value? You don't. Yeah, it's all trade-offs. It's all trade-offs. So and they're for a higher reliability system, you're going to want to use more reliable radiation vetted parts, and it does cost more. So there's a risk cost trade-off when you're doing your evaluation. So if it's a university project, you're probably going to put up maybe a cell phone. if it's something that you're trying to collect actual data and perform a mission for a certain amount of time, you definitely want some confidence that spacecraft is going to perform over that mission life. Thanks everyone for attending. Appreciate it.